Welcome our next speaker, Ms. Cheryl Duguid from GT Advanced Technologies. She's the Vice President and General Manager of the Sapphire Equipment and Materials Division. She will be speaking about defining the sapphire metrics that matter, a data-driven approach. Ms. Duguid brings over 20 years of international leadership experience in multi-billion-dollar industries, and she specializes in the commercialization of innovative, high-efficiency, energy-saving lighting technology. 接下来的演讲者为吉特先进蓝宝石设备和材料副总裁兼事业总经理 Ms. Cheryl Duguid。今天的演讲主题为定义蓝宝石度量标准，一个数据驱动的方式。Duguid 女士担任在 GT Technologies 担任要职，拥有超过20年余的国际企业领导经验。她特别专精于高效能和省电照明产品的市场策略。Let's welcome Ms. Duguid.
Hello everyone. As a backdrop, I'd like to provide an overview of GT Advanced Technologies' Sapphire business. GT entered the sapphire industry last year through the acquisition of Crystal Systems, a company that had been supplying high-quality sapphire material to the LED industry and specialty markets for well over 40 years. Since the acquisition, we have tripled the capacity of our sapphire materials factory to approximately 6 million TIE, or 2-inch equivalents. We've leveraged the combined strength of Crystal Systems' extensive crystal growth experience and industry-leading ASF technology with GT's capital resources and equipment manufacturing expertise to develop a very successful sapphire equipment business where we sell our advanced sapphire crystal growth, or ASF, to sapphire substrate producers. At the core of both our sapphire materials and sapphire equipment business is our ASF technology platform, a highly automated sapphire growth process that has been optimized for the high brightness LED market and is proven to produce very high quality, high yielding sapphire material. We have long heard from our sapphire material customers, many of whom are in the top LED wafer manufacturers in the world, and from our customers' customers, that the material produced by GT ASF technology is of the highest quality. To verify and quantify the feedback, GT initiated an extensive material characterization project to study our material performance throughout the entire LED value chain and identify what sapphire metrics matter most for the high brightness LED manufacturing. This design of experiments is illustrated on this slide. Many of our customers that over the years have bought material from Crystal Systems refer to the material as the best, we like it, it works well. But when we attempted to get the customers to try and quantify what those terms meant, it was very, very difficult. Also, as you've probably heard today, in this fast-growing LED market, there have been a lack of standards. And so we had two objectives here. One was to try and quantify what our customers were telling us, and also to try and help understand what were the key important ingredients in manufacturing sapphire and the materials outcome of that furnace growth that really were going to impact the light bulb itself. We designed the experiment based on a systems approach with an understanding of the LED manufacturing process. Analysis are performed to identify and evaluate the sapphire material inputs, their effect on the LED manufacturing processes, and the outputs including yield at all stages, as well as wafer quality and all the way through LED device performance. The project itself includes many initiatives, some that are complete, and others that are underway. Today I will present the findings of our LED wafering study, here, and some research that we have done to evaluate what impact, if any, sapphire color has on the LED manufacturing process. So our wafering project experiment design, which you can refer to on our website, it's been published on our website, included wafer metrology, EPD or etch pit density data, and wafer rejections. All wafering was performed by an independent top epi-ready wafer manufacturer. Analysis of blind samples of sapphire from GT and 3 other suppliers and alternative sapphire growth technologies. In total, 25 cores were evaluated over 1,500 millimeters of 2-inch sapphire. 13 of the cores were from GT's library of varying material grades. 12 cores were from other suppliers, all provided as LED grade material by the originating source. Internal to GT, we use a method called OHT. For further details of this grading method, you can be found on our website where we've done a white paper on OHT, but it stands for Optical Homogeneity Technique. And GT found that OHT is more robust, conservative material qualification method. OHT is a material quality grading technique that determines the crystalline quality and gas content, or bubbles, for sapphire material at the boule, the original material level, and at the core level. All of the unmarked cores, all 25 of them, were inspected and graded by our certified technician using the OHT to identify material that is above or below GT's acceptable material standard deemed LED grade. And as you can see from the chart, even though the alternative technologies had supplied material that was deemed LED grade, when we had our certified technician inspect it using the OHT method, he actually rejected some of the material. In addition, we included from our ASF material that we knew was rejected and not LED grade material. This is not typical of our ASF process, but we wanted to make sure that we had a full statistical sample. Surprisingly, OHT detected critical defects on some material that had passed as LED quality by the customers, and these are highlighted. Etch pit density, or EPD measurements, were taken on a statistically significant number of wafers pulled from each core. EPD has traditionally been used as the method to separate or identify LED and non-LED grade material, and it is done at the end of the wafering process on a very small sample of the core, and therefore it is a destructive test, and it is done after the wafer house has spent all of their capacity, quality, processing to process the material. Wafers that were found to have an average EPD above 1,000 pits per square centimeter were identified by us as non-LED. That's a pretty standard industry practice. EPD measurements, in this case, missed 6 cores that were identified as non-LED, meaning we had rejected them as non-LED, and using the EPD method, they would have passed and been processed onto the epi house where they would have failed and they would have been rejected. So the LED wafering analysis processed all 25 cores through the standard wafer manufacturer's process, shown here, including sawing, lapping, annealing. As this was a blind study, the wafer house did not know the source or quality level of the sapphire core material. So they processed all the material independently of knowing what the source was or what our results had shown through our OHT or EPD method. Standard wafering specifications, they do a number of quantitative tests after the annealing process. And typically, after the standard annealing process used by all wafer houses to remove the stress induced by the sawing and polishing process, measurements are taken for roughness, total thickness variation, total warp, and total bow. This shows the total average results for each of the sample sets, GT and the other competitive technologies, and the average results for each of these measurements. And then we rank them based on that average. In this case, results ranked based on average results, GT ASF material ranked number 1. One of the critical economic criteria for a wafering house is yield. Simply, that's the amount of millimeters of core or millimeters of sapphire material to start with. How many good wafers do you get at the end? And so one of the criteria that we used was to have the wafer house supply us with the yield of the cores through their whole process. And the percentage of rejected wafers to yielded wafers was tracked by the third-party wafer manufacturer using blind sapphire wafer samples. In this case, again, using the average yield, the ASF material had the highest wafer yields at 97.8. If you combined these 3 criteria that we measured, meaning the EPD average count, the wafer analysis ranking results after the annealing process, and the final wafer yields, and you rank those, you see that the GT ASF ranked number 1 as far as the criteria and metrics that matter to the wafering operation. So in summary, these are statistically significant and quantifiable differences between sapphire materials with different growth technologies. The OHT method proved more conservative and capable of identifying material rejects over EPD and method used by other suppliers at the core and wool level, meaning the material was identified as LED grade or non-LED grade before it went into the wafering process and before the wafering house spent money processing the material. GT ASF material performed the best on overall performance based on the EPD results, the wafering metrology, and the rejected wafer ratio. Wafer yields matter, and GT ASF material ranked number 1 for wafer yields. Another part of our study focused on the issue of color. There has been a lot of discussion, both in the press and through discussions at seminars, about color and the potential impact that it might have to LED quality. Naturally, we wanted to identify the quantifiable impact, if any, on the yield and economics on the LED supply chain. Again, focusing on measurements, data, science, and as part of our complete DOE, or design of experiments and characterization study. The first thing we did was to actually measure color. And using GT has performed extensive studies on material color and color properties. Measurable, repeatable data shows that all of the samples we had from all the different sapphire growth technologies, that all the material has color. Competitors' material was measured to have a more yellow hue than GT material, which had a pink hue. Yellow is less noticeable than red under typical industrial lighting conditions, and purely visual inspection is not able to identify and differentiate the color differences. So if you look at this is the sample set, again using the same sample set that we used in the wafering yield study. It was a blind sample. We had our certified technician use metrology equipment to actually measure the color. You can see this is ASF on the pink side, And this is the other competitive material and competitive growth technologies of the yellow. If you look at the standard wafering process at all the major wafering houses, the material, the core material from the original boule is sent through the sawing wafering process and goes through an annealing process to reduce the stress that is imparted during that. And what we were able to find was that pink color in the ASF grown material is a byproduct of a high-yielding growth process optimized for LED weight manufacturing, where light transmission approaches 100% of theoretical maximums in the visible spectrum at the pre-anneal wafer level. Standard epi manufacturing process calls for post-annealing at the wafer level to relax stresses induced during grinding and polishing. Annealing at wafer level is a standard step in LED wafer manufacture, taken for any and all sapphire. One common concern was that color is caused by contamination. So one of the critical analyses we performed was to measure the raw material, or the aluminum oxide, for contamination levels, and then measure the actual sapphire crystal after the crystallization process and measure the contamination levels. What we found was that during the ASF growth process, there is no additional contamination of the sapphire, meaning the contamination levels before and the contamination levels after are exactly the same. So we don't put any contamination into the sapphire crystals. The other thing we found was that ASF grown sapphire exceeds purity levels by epi-ready wafer manufacturers, meaning most standard wafer houses, the standard for sapphire contamination is 99.995. And so in using GDMS, we analyzed a large sample of our material, and we were able to determine that the sample of material had an average purity which exceeded the 99.95 or less than 21 parts per million. And that the normal suspects that might have caused the pink color, meaning chromium, molybdenum, iron, titanium, or magnesium, were at levels that were barely detectable. So we determined that contamination was not the cause of any of the color. So in conclusion, what does matter based on both of these studies? Color is not a relevant measure of quality for ASF grown sapphire. Pink, or the light pink hue that you see, is a byproduct of a high yield process optimized for LED manufacturing. Color is removed during the standard epi wafer annealing step, and ASF pink is not indicative of impurities or contamination. Potential defects in bulk sapphire cores that do have an impact on LED manufacturing include bubbles, low angle grain boundaries, inclusions, and crystal twinning. The GT-ASF growth process dramatically minimizes bubbles. And the OHT method is proven to effectively detect these defects. We at Crystal Systems do not ship product with these defects or with any inclusion zones in our cores. Sapphire performance on key LED wafering parameters such as smoothness, total variation, warp, and bow do matter. They do impact the yield of the wafering houses. So the metrics that do matter are yields matter. Sapphire material has a direct impact on wafer yields, or the profitability of the wafer houses, in other terms. And ASF grown sapphire ranked #1 in wafer yields. So what's next? We will continue to test and quantify our materials and processes, along with the other competitive technologies in a blind study analysis, so that we can deliver the highest sapphire quality and yield to our customers. We have several other initiatives underway, many in partnership with leaders in the LED industry, to continue to define what are the metrics that really matter in evaluating sapphire quality and how GT material stacks up. We are uniquely positioned due to our Salem facility and the capacity and capability we have there, and the in-house access to material, and combined with the direct feedback from a number of our customers. Thank you.